Hello, my name is Chris Johnson, and welcome to my video lab report for Lab 3, Black Hole for Physics 2211. In this lab, I'll give an overview of the problem first, explain the related physics concepts, and then explain how I apply the physics concepts into GlowScript, and answer the what if and what does it mean questions at the end. I'll do this for both Part 1 and Part 2. The first problem is finding the mass of a black hole by observing the motion of an orbiting star. This is backwards of what we've done in our previous labs, as we have been predicting the future motion of an object given the mass and the net force. We will do this by first identifying the system, use observations to find the net force acting on the system, using those observations to specify the interactions causing that net force, and finally solving for the unknowns, in this case the mass of the black hole. To begin, I made some initializations to set the time, mass, and unique trajectory. After running the code and viewing the original trajectory of the star, I concluded that Fnet is due to the singular force of gravity, or the gravitational force from the black hole. To find the mass of the black hole, we will use Newton's universal law of gravitation to describe the interaction of the black hole and the visible star. Rearranging the equation allows us to solve for the mass of the black hole. First things first, we need to find the magnitude of the net force acting on the star, or Fgrav. How can we do this given just the motion of the star? Let's simplify this in terms of only 3 positions for now. With R0 and R1, it is possible to find the velocity. I repeat this step with R1 and R2. Now that I have 2 velocities, I can find the change in velocity, which we know is acceleration. We can now use Newton's second law to find the net force by multiplying this by the mass and dividing by the change in time. Our code will allow us to iterate the same process across each of the star's observed positions. So how exactly do we do this in code? After using lists to find the x and y components of our new velocities in line 131 and 132, we create a while loop to step through all the position data points using index as the loop variable. For each position, we calculate the x displacement first in line 137, then in line 38 we calculate the velocity in the x direction by dividing displacement over the change in time. We do the same thing for the y variable in the same loop. With all the necessary data and code in place, we can calculate the net force from the motion data. We begin by sourcing our initial velocity by subtracting 1 from the loop variable and source our final velocity as well for each time step in lines 160 through 161. Then we find our momentum by multiplying the velocity by the mass of the star. From these we can easily find the change in each, or delta P, delta T. In line 172, we are able to use the fundamental principle of Newton's second law to find the net force. In line 180, we are able to find the parallel component of the net force by taking the derivative of the magnitude momentum with respect to time and multiplying it by the unit vector of momentum. Because we know the parallel component and net force, we can find the perpendicular component through the transitive property in line 186. We use the original gravitational force equation to calculate the mass of the black hole in line 193, and then we run our code. We can see our force vectors making sense, as well as our code outputting the mass of the black hole through every iteration. I average this in Excel to get a final mass of 1.04 times 10 to the 34th power. In response to the what does it mean question for part 1, according to Newton's second law, the unbalanced net force applied on the object is directly proportional to the rate of change of momentum. Hence, we found that the rate of change of momentum is equal to the net force applied on the object. The perpendicular and parallel components add up to be the net force, but without each other, they do not make the rate of change of momentum. Moving on to part 2 of the lab, I crashed my rocket on a planet orbiting the black hole from question 1. I need to escape around the black hole without being pulled into the orbit of the black hole. What initial velocity does my ship need to have to avoid the black hole and get off the planet? Using the starter code, I brought in the mass of the black hole as found in part 1 in line 31. I used Newton's universal law of gravitation to find Fgrav on the planet from both the ship and the black hole. For the sake of time, I'll give a brief overview of the code for one Fgrav calculation, as the others follow the same processes with different interacting variables. To find the net force of the black hole on the planet, I first calculated the distance between both in line 73. I took the magnitude of that distance in the next line, then I found the unit vector of that distance to plug into the gravitational force equation in line 76. I did the same thing to find the net force on the spaceship from the planet and the net force of both the planet and the black hole on the ship. Given the net force acting on both the planet and the spaceship in line 102, I can now iterate through different velocities until I find the one that will allow me to survive on this mission using the position update formula in line 109. I found that if I were to begin with initial velocity vector of negative 10 times 10 to the 6th x, 10 times 10 to the 6th y, 0, I would successfully get off the planet without being sucked into the black hole. In response to the what does it mean question, my spaceship would have to travel at an initial velocity of negative 9 times 10 to the 6th x, 9 times 10 to the 6th y, 0z to orbit the black hole instead of simply avoiding it. That concludes my video lab report on Lab 3, Black Hole. I hope you enjoyed and thank you for watching.